All right, in this second to last example, we look at a rational function which is not really in the usual form of a rational function as a fraction. This is a polynomial plus a fraction. But we said last time we can combine this using getting a common denominator, taking this x and multiplying it by x over x to get x squared over x, add them, and we get x squared plus 3 over x. So now this is it looks like a normal rational function. Okay, the domain will be every number except 0. X squared plus 3, there's no way that this can ever be 0, right? Because x squared plus 3 is always going to be at least 3. So there's no x-intercepts. Because 0 is not in the domain, there can't be any y-intercept. The vertical asymptote is at 0. And because the degree of the numerator is bigger than the degree of the denominator, there's no horizontal asymptote. And as a point, this numerator is always going to be positive. Okay, so we can see the only time that this will change sign is at 0. That's when x changes sign. So it's going to, when x is positive, we have a positive divided by a positive. When x is negative, we have a positive divided by a negative. So it's below the x-axis and above the x-axis. And so the graph is going to be very unusual. It's going to look like the, well, we at 0, at this vertical asymptote, we can see that we're shooting down, and then we're shooting up. We're shooting down on the left, we're shooting down on the right. And because the graph has to be below the x-axis when x to the left of 0, we have to turn around at some point here and shoot down. Shooting down, that's not leveling out because there's no horizontal asymptote. So it shoots down. And the same thing happens above. The graph has to be completely above the x-axis to the right of 0, and it's going to shoot up on the right. So it certainly it has to turn around at some point. We don't know what the coordinates of the turning points are. You will find that out if you take calculus, but you don't have to worry about what these points where these turning points are, just that they exist. Okay, for our last example, we're going to go in the other direction. We're going to take a graph and see if we can come up with a formula or a rational function to match this. So once again, it's really about, just like with polynomials, we just needed to know the x-intercepts. Here with a rational function, we just need to know the x-intercepts and the vertical asymptotes and the horizontal asymptotes to some extent. So in part A, we can see our x-intercept. We only have one, and that's at 2. We have a vertical asymptote at -1. Okay. And we have the horizontal asymptote is at y equals 1. Okay. This tells us that x minus 2 has to be a factor of the numerator, and x plus 1 has to be a factor of the denominator. Okay. So x plus 2, x minus 2 over x plus 1. Okay. And then we just have to check, okay, the fact that we have a horizontal asymptote, which is not there you go, that's not the x-axis, means the degrees of the top and bottom are the same. So then, in fact, they are. Okay. And in fact, then we just have to make sure that there's positive where it's supposed to be. And, we can do a very quick sign chart on this. And we can see on this particular one, it goes from positive to negative to positive. Okay, which is exactly what's going on here. So we can let r of x just be this. X minus 2 over x plus 1. Are there other answers? Yes, there are. We could multiply this by any non-zero constant as long as we do. So we could multiply by 3 and divide by 3. we could also make this x minus 2 to the third over x plus 1 to the third. Okay, but because this is but we couldn't multiply by any other factors like x plus 2 or something like that. If we look at part B, we have one x-intercept at 0. We have a vertical asymptote again at -1. All right, and then we have a horizontal asymptote at y equals 0. The fact that y equals 0 is a horizontal asymptote, that means that we need the degree of the bottom to be bigger than the degree of the top. So once we know that x minus 0 has to be a factor of the top, x plus 1 has to be a factor of the bottom. Okay. Now, however, this is going to have a vertical this is going to have a horizontal asymptote of y equals 1 because the degrees are the same. So we want to increase the degree of the denominator, and for a couple of reasons. One, because of the horizontal asymptote, but also because of the fact that we don't change sign at -1. So we're going to put a square, x squared here, x plus 1 squared here. Okay. Now this will have a horizontal asymptote at 0. And we can check that, in fact, that this will be, we can make a sign chart for this. By the way, this simplifies to x over x plus 1 squared. And we can see the denominator will always be positive. The numerator changes sign at 0. So in fact, it satisfies this. We could make a sign chart, and we see this will be negative, negative, and then positive, which is what we want it to be. For the last example, we have an x-intercept at 1. We have a vertical asymptote at x equals -1 and x equals 2. And the horizontal asymptote is y equals 0. Okay. So this tells us that we need an x minus 1 to be a factor on top. This tells us we want x plus 1 and x minus 2 to be a factor on the bottom. This last part says that we want the degree of the bottom to be bigger than the degree of the top, and sure enough, if we were to multiply this out, we'd have x squared down here would be the first term. So the degree of this is 1, the degree of this is 2, so that's good. And you can check that it's going to be the sign of this function. This changes at -1, 1, and 2, and you can do a sign chart for this. Plugging in numbers on each of these intervals, and you can see it goes from all right, so we see that. Let's before we go any further, let's just do a sign chart on this. We can see that this does not change sign at 2. So this 2 corresponds to this x minus 2. So we really need this to be squared, okay? Because otherwise, if we don't have this 2 here, we'll have this will change sign at 2, which we don't want it to do. Okay. It does change sign at 1. It does, so we leave this here. It does change sign at -1. So with this we don't need an exponent here, but then this works because we can see that this is positive. Starts out positive, then negative, then positive, and positive. Okay, so this should work. It's basically kind of what we're doing with finding polynomials. Okay, remember the factors of the numerator correspond to the x-intercepts. the factors of the denominator correspond to the vertical asymptotes, and then we just check and see, does the function change sign there? If it does, we need an odd multiplicity. If it does not change sign, we need even multiplicity. And of course, we could change this 2 with replace this 4 with a 2, or we could replace this 2 with any even number, and we could write x minus 1 to the third if we wanted to, as long as we did that here, keep the degrees the same. All right.